For this group project, we were tasked with recreating Osborne-Reynolds' experiment to study and show the three different conditions of flow in fluid pipes. Osborne-Reynolds developed his equation to find what is now known as the Reynolds number, to relate the characteristics of a fluid to the properties of a fluid, using this setup known as the Reynolds experiment.
So what is the Reynolds number? The Reynolds number is a unitless number that easily identifies the characteristics of a moving fluid. It also accurately estimates how a fluid will move and act under certain conditions. So it's really important for identifying flow characteristics, especially in pipes, whether it's flowing very slow, medium, or very fast. And there are particular characteristics of fluids that we're predicting, which will be explained later in this PowerPoint. But the main idea to grasp is that it's a unitless number that just describes the flow of fluids through either pipes or some kind of fluid structure. So the Reynolds number formula is a very simple formula. All it is the Greek letter rho times velocity v times diameter of a pipe d, the inner diameter, all over the dynamic viscosity. Something very important to keep in mind when considering the Reynolds number is that the Reynolds number is defined at a particular temperature of that fluid. So the Reynolds number, for example, oil at room temperature would have a different flow characteristic, say if oil was at 100 degrees Celsius. And that's just describing, and that just has to do with the properties of the fluid itself. But the Reynolds number is just that number that also characterizes the fluid's flow properties as it's in motion. So yeah, this is essentially the Reynolds formula, very simple formula, but it's also hiding a lot of very important concepts regarding the fluid's properties and other characteristics.
What are the three different types of turbulent flow, you might ask? Turbulent flow is when the flow of a fluid is chaotic and unpredictable. To get turbulent flow, you need a Reynolds number greater than 4,000, where laminar flow is the complete opposite to turbulent flow and is very streamlined with a more predictable pattern usually found in slower moving fluids. These have a Reynolds number of less than 1,200. Right in the middle is transitional flow, which is a mixture of slightly streamlined but also a little bit more unpredictable at the same time, with a Reynolds number being between 1,200 and 4,000.
For our experiment, we sought out to recreate and prove the accuracy of Osborne-Reynolds' experiment and to provide first-hand visual evidence of the definition of Reynolds number and the classification of fluids. From Reynolds' original testing apparatus, there are many similar aspects built into our recreation. First, there is an ink reservoir placed at a greater height from the rest of the apparatus. This is to apply a more pressure head to the ink to overcome surface tension and the static pressure of the water. Red ink is used to provide a greater contrast between the observed path and the rest of the fluid. Next, there's the observation tube, where the fluid, water, is released through it at varying rates. This allows us to observe the effects that a fluid's velocity has on the classification of the fluid. Because of the tube, we can observe the fluid across a larger distance to show whether the fluid is steady or not. To allow a steady stream of dye to be injected into the observation tube, a needle was placed just inside the mouth of the tube so that the observers can visualize the classification of the fluid.
In addition, there is a funnel that was placed at the mouth of the observation tube to allow the fluid to smoothly enter the tube for accurate visualizations. For our first trials, 1 and 2, we aimed to reach a laminar flow, which should be visualized as a steady line throughout the observation tube with minimal mixing between the water and the dye. Here is the result from our first trials and our replica of Reynolds' experiment. As expected, there is a steady stream throughout the entire length of the observation tube. Using this information, we can conclude that this flow is laminar. After laminar flow, in our third trial, we aim to see the visual representation of transitional flow. The expected behavior is a streamline where the tail end breaks from the streamline and begins mixing with the water. In our experiment, the dye was visualized as expected. There is a streamline in the beginning of the observation tube, and as the distance increases, there develop swirls named eddies, which cause the dye and the water to mix further down the tube. In our final trials, we aim to reach a turbulent flow. We expect to see many eddies in the fluid and rapid mixing throughout the entire observation tube. In the end, we were successful in achieving turbulent flow as the ink mixed rapidly and is fully saturated into the fluid by the end of the observation tube.
I would like to take a moment to briefly cover our calculations. Density and dynamic viscosity of water are temperature-dependent properties, so after testing the temperature of the water, we consulted with various tables to determine what the most accurate values for these properties would be. The measured inner diameter of the tubing was already known, and area was just a short calculation away. As seen in trial 1, we recorded the time to fill up a bucket in gallons per minute, and converted it to cubic meters per second, which was our volumetric flow rate. We derived velocity by dividing the volumetric flow rate by the area, and Reynolds number was calculated as previously discussed. The same process was conducted on the rest of the trials, and it is seen that the calculated Reynolds numbers align with the visual representations obtained previously, thus proving the validity of Reynolds equations and their respective applications. In conclusion, we were able to recreate Reynolds' findings by visually representing each classification of a fluid while also proving the equation used to determine Reynolds' number. Using this knowledge, we can be certain that the calculated Reynolds number is accurate within reasonable error to the actual characteristics of the fluid. Thank you for taking your time to watch this video, and we hope it greatly assisted you in your learning experience.